This is a program and will not be executed by itself. It's like a cooking recipe. The program will be written by the programmer and stored in the hard disk forever. And the recipe may be in the drawer. In order to make this dish, we need to take out the recipe, put it on the table, and then follow the steps to make the dish. This is equivalent to that the CPU reads the program from the hard disk to the memory, which is convenient for the CPU to read. The executable program instance in memory is called a process. If a program is read into memory multiple times, it becomes multiple independent processes. When multiple programs in the hard disk are read into the memory and run, of course, more processes are created. Any place in the memory has a corresponding address for easy access, and each process in the memory has a virtual independent address space inside. In the process, it can be accessed based on the virtual address. How do you access between processes? First of all, the process is the complete unit of program execution, so most of the time is in the process. Inter-process communication (IPC) is needed among processes. This may require a system call. The access will be slower. We will not explain today. Each process thinks that it owns the entire memory and does not need to care about the actual location of other processes. This separates the processes very well. For each process, there is a program loaded first. Usually there's only one program counter, which records the position of the current program execution and will be calculated in accordance with the program sequence. An execution flow here is a thread. If there are multiple threads, multiple program counters are needed. Each thread will run independently. In addition, each thread also has status information, such as registers and stacks, while the program is running. At the same time, the information shared between threads is address space, global variables, open files, and so on. Then why is there a smaller process thread in the process? Suppose this is a document editor. Naturally, it is a process that stores the corresponding programs and documents. Now the user uses the keyboard to hit a carriage return at the end of the second line. We need interactive programs to accept the keyboard press events. Then the layout program recalculates the positions of the text and then renders them. In addition, at regular intervals, the writing program saves the document to the hard disk. Therefore, these three programs should be able to execute it in parallel. But they need to access and modify the same document, so they must be in the same process. Therefore, three more lightweight threads are needed at this time. Now we understand that thread is the smallest unit of parallelism. If the computer now has only a single core CPU, it can only execute one thread at a time. Then each thread needs to be executed in turn, and the time for a single calculation each time becomes a CPU time slice, which is actually only tens of milliseconds. Users can't feel it at all. Then for a thread, when it is waiting for the CPU, it is called the waiting state. Once the CPU comes to execute, it changes to the running state. When the CPU shifts to execute other threads, it becomes waiting again. If the thread is executing, the program sends an access request to the hard disk and then waits. At this time, the CPU becomes idling. Therefore, the thread becomes blocked. The CPU then executes other threads. Wait until the data from the hard disk is restored. The thread changes from the block state to the waiting state, waiting for CPU to come again. Then continue execution. If it is multiple CPUs, multiple threads can indeed be calculated in parallel. However, there are often many threads, so time-slice rotation is still needed. So in order to simplify, the CPU is in the kernel and provides its own virtual CPU for each thread. Each thread will think that it is always monopolizing the CPU. They do not need to consider the question of time-slice rotation.